Okay, let's get started. Let's jump in. But any questions so far? Good. So let's continue with Dirac Lagrangian. So previously we talked about construction of the Dirac Lagrangian, right? And then for this is a quick summary of what we have done so far. And we demanded that theory has also parity, not only Lorentz invariance, and then that told us that we have to introduce both Felicity states, right? That the parity exchanges those. We talked about the choice of proper phases to make it Lagrangian invariant. And then eventually we landed on the following expression. So we had a Lagrangian for one of the helicity states. To fusion it up, we show, I think, that this has a negative helicity, right? And then we also have a term, that. Now, on top of that, we also added one extra possible term. As again, we showed us on how this part can be made parity invariant, meaning there's always choice of a proper definition of parity such that this mass term, called the Dirac mass, is parity invariant. So I think that's sort of we left off. But where exactly did I leave the lecture? Okay, did I derive the Dirac equations and start talking? Not yet, right? Okay. Good. So then, now today we're going to study this system and then actually solving Dirac equations and learn about the physics of classical solutions to this theory. Okay, so that we sort of did already. Now we can immediately derive a equation of motion from this, which no surprise. For instance, we can look at the equations of motion for u plus dagger, and that will give us that term from the kinetic term, and then from the mass term that will give us this. Then immediately the same way, we can also derive the Dirac equation for u minus dagger. That's that. That will give us. So from these equations of motion, which we will show that this will indeed play the role of mass, right? One thing that you immediately see is that now equations of motion mixes up plus equation with a minus and then a minus with a plus, and they're mixing exactly came from this math, which will show mass. Okay, so introduction of this math Dirac mass, which was not surprising because this was exactly the term that mixes u plus with u minus and vice versa. Okay, so next mass mixes up to different helicities. Good. But before that, as we have done before already, this can be used to show immediately that they satisfy, as expected, Klein-Gordon equations. Okay, so how do you do that? Well, you can do it either way, but here I'm going to do it quick way. Okay, and so how do you do that? Well, take this equation. So take one equation, because the other one is exactly the same procedure. Take this equation, and then you can multiply this equation with I now sigma nu L nu. So why am I doing that? The motivation is this. So this is a coupled equation that you have learned from the Maxwell's equation. Good strategy to solve the equation is somehow get the decoupled equation, right? And starting from the first order differential equation, which is a coupled, we can get the decoupled, the second order differential equation. Okay? So that's what I'm doing. By multiplying by this, I'm anticipating that this acting on the right-hand side, according to the second equation, will get me back u plus instead of u minus. Okay? That's how we do. Therefore, let me write some minus of sigma nu, sigma bar mu, del nu, del mu, acting on u plus will be, now using the second equation, give me m squared u plus. So here we go. So now we got equation which is second order rather than the first order, but nevertheless, now this is a decoupled equation, right? This is equation only of u plus. you can do the exact same thing on the second thing. You get the equation which only has u minus the second order differential equation. Now, this thing has some several useful, also important identities. But one of the identities that this satisfies is that if you anti-symmetrize these indices, by which I mean you have this minus the other way around, right? So if you do that, I won't actually symmetrize because this derivatives are manifestly symmetric, right? Under the exchange of indices, I want to look at the symmetrization. And this will be equal to, this is 2 by 2 matrices, 2 times metric, and then two-dimensional identity operator acting on this two-dimensional space. Okay, so we will talk a lot more about this sort of identity today and the next time. Good. Sorry, was there a question? No. Okay. So now, if you do that, so what am I doing here? So given this, of course, systematically, obviously, this can be decomposed into a anti-symmetric part, and then the symmetric part that I was trying to look at. So, and then I know that this particular symmetrization gives me 2 times eta mu nu. So you see that that equation therefore turns into nothing but minus del mu u plus is equal to m squared u plus. Okay. And obviously, this is what you expect, because this is nothing but Clay-Gordon equation, and showing, importantly this time, that this parameter n that we introduced an arbitrary possible term which multiplies additional Lorentz invariant quantity, indeed, takes the interpretation of the mass for this particular field. Okay, so that's what we learned. Good, let's move on. All right, so then I'm going to rewrite this a little bit. So this Lagrangian can be rewrite in a slightly compact, nice, useful way. So at this point, I'm just gonna rewrite, okay? But then later on, we will start understanding deeper meaning of that rewriting. Okay, so far I'm just gonna rewrite. How do I do that? First, I introduce a Dirac spinner. Okay, so here I'm gonna use notation that there's a Dirac spinner, which I put u plus and then u minus like so. And in case you remember, if not, doesn't matter, you just follow what I said. You remember this u plus is a 2-component spinner, so it has a 1 and 2. And then I also sort of introduced this notation, a alpha dot, even though I didn't went through comprehensively. Yes. So by which I mean, I'm just going to compose now 4-component column vector looking object. Upper 2 component comes from the negative velocity to state. Down 2 component comes from the positive velocity to state. Okay. So this guy were either left-handed or velocity minus n. And this second downstairs is a right-handed or velocity, etc. I'm just putting them together. Okay, so far it's a notational introduction, just the introduction of new notation. Okay, and then the claim is that, as you can check, this direct Lagrangian can be written slightly more compactly as I, that's to start, so I is a good start, psi d dagger, time derivative, and then alpha, which I will introduce, but I mean this minus m psi dagger, and that's psi, and then I have all these there, where alpha vector, in this notation, I will put some notation momentarily, minus sigma matrix 0, 0, sigma, and then beta, in this case, is 0, 1, 1, 0. Okay, so this long expression, at least, has been shrunken to a little bit shorter expression by introducing a 4-component spinner called Dirac spinner, which has both velocity state, and then introduce these two notations. But then they will take the deeper meaning momentarily, and then we will investigate. Yes?
In the beta, 1 means identity matrix by.
That's right. So this is a 2 by 2 identity matrix sitting. So this is like 2 by 2 block, each of them. Okay, so it's just like sigma is 2 by 2. Okay, and then here I'm gonna actually put W. For now, I mean, it shouldn't mean anything to you because I introduced a lot of notations. So what's wrong with putting extra notations? I'm doing. Yes.
But is M okay to be negative? Because it essentially appears as a unit.
Right. So good. So what actually appears in the Klein-Gordon equation is whether it is a plus or minus sign, it will anyway appear as a square of that parameter. So long as equations of motion in a dispersion relation, by which I mean E squared is equal to P squared plus M squared, that is concerned, it looks the same. Now, that doesn't mean that this minus sign or the sign of the M is unphysical. Sometimes it is actually, it can be physical. But the way we arrived at this point, if you remember, was that I start out with arbitrary complex parameter, and then I said that I can always do field redefinition of either U plus or U minus, doesn't matter, so that I can just rotate away any sign in front of that, including possible bases when we discuss the parity. However, there is some context where the sign matters, okay? And that's when the choice of sign has a non-trivial relation to the symmetry, and that symmetry has non-trivial anomaly. Okay, I'm going to just throw out a bunch of words. So sometimes sign matters, once again, if there is a deeper symmetry reason where this is linked to some symmetry, and then that symmetry has anomaly. So depending on the sign, you get different sort of bases of quantum field. But at this point, we're just going to take a simple-minded approach that I just have a full ability to make arbitrary field redefinition. Once again, I mentioned to you that in some cases, especially quantum mechanically, arbitrary field redefinition may not be allowed to do. But here, I'm not worrying about the quantum effect. Okay. Then classically, I can always get to this point. And then quantum mechanically, once again, anomaly, blah blah blah. Non-trivial business can be there. The sign may matter. Okay. Good. So, okay, what are these W's? So these W's means vial. So in particular, here you see a concrete explicit expression for alpha and the beta. And then we're going to call this particular expression to be vial representation. You might say representation of what? Which I will introduce. But I'm just going to introduce this wording now so that later when you hear again, now it's slightly more fun. Okay, so far, what I have done is almost nothing. I just rewrote. I introduced a whole bunch of the notations. Now, we really try to understand the meaning of those notations. Okay. Any questions? Good. Now we're going to solve these equations and understand the different meaning of yes.
The Lagrangian is just meaning of the spin one half representation of the function. Am I right?
Good. So yeah. So this guy had spin half. Indeed, the spin half is not correct word because this is massive. And then, if you like, slightly more technically correctly, it is direct sum representation of this. Okay. Any other questions? Yes.
Is unique representation of this group or not?
So this is already a representation of a Lorentz group, and your question can be, I don't know if you want to take that as your question, can be, if I want to say that I want to have a spin half representation, is this a unique option? That can be your question. So by that, if I demand that, can I have a dimension? This is dimension 4 representation. You can ask whether dimension 4 representation with spin half is uniquely this, or can be something else, right? So that can be the question. The answer is this may not be necessarily a unique answer. However, as we started out, if you, for instance, impose a parity in addition to the Lorentz invariance, then this will single out this as a unique representation. We will have a discussion about this later. Okay. Good. Okay, so let's study this Lagrange better. So now, you see in quantum field theory, okay, this is a way of writing this Lagrange, right? But then obviously I can choose a different basis for this field, right? I can have the expression for Lagrangian. I can make a change of basis, right? Meaning I can decide to use different form of my field, but the physics shouldn't carry shouldn't change. That's because I changed the basis of the description. So just to be totally consistent with my notation, again, this subscript here, W, I use that to say that I am in a particular basis of a description of physics. In this case, for instance, I can call it a Weyl representation, but I can also call I'm in the Weyl basis, if you like. So just so that it's totally consistent, let me actually switch these, which was introduced to say it's Dirac, but actually let me switch to W everywhere. So I'm in the W basis. Okay, good. I mean, done. Right? Wait, this is for the really Dirac fermion. Okay, Dirac fermion that I cannot I keep it. Okay, so I'm in the Weyl basis of this group. Now, the basis that Dirac first introduced is not exactly this. And we can make a change of basis. Okay, and so here we're going to talk about Weyl versus Dirac basis. Or later on, we're actually going to talk about the representation on something, which something has not been introduced. So what I do is that starting from the Weyl basis, this 4-component spinner, I'm going to make a change of basis by multiplying it. So now I'm going to define U basis. Now D is really name tag for the basis. Okay, is some invertible matrix times that thing. This is T is a 4x4 invertible matrix that achieves change of basis. But then, in order for the Lagrangian to be invariant under the change of basis, right? So that it takes the same form. What do I need? So basically, this Lagrangian takes the form that there is a column vector, row vector, and then 4x4 matrices. Okay, and then column vector, row vector, 4x4 matrices. Okay, so it's sandwiching. You see that, therefore, then this is invariant if we also perform, for instance, starting from this Weyl basis alpha matrix to T alpha W D, and let me just call that to be alpha D, just to be consistent. And then likewise, I can also take Weyl basis or Weyl representation W, exactly the same T, beta inverse, and then I'm going to call that to be beta in the Dirac basis. And then you can work it out explicitly how that looks like by just taking a specific choice of T. So if I take a T to be, so let's take a specific choice of T. So let me take a T to be 1, minus 1. This is well defined for 4x4 invertible matrix. If you do so, this will take the form that U plus U minus U plus minus U minus. Okay, you can just work it out. Okay, no problem. And then again, starting from the expression that I wrote down there, if you work it out here, then you get 0, 0 minus sigma. No, stop. Full stop. Stop. Like so. Right? And then beta in Dirac basis, just to make sure, 0, 1, minus 1. Okay, so I just literally made a change of basis, and hopefully you're convinced that Lagrangian doesn't change under that change of basis. Okay, I just literally made a change of basis.
Professor,
Yes.
I have a question about in the Lagrangian we use it Hermitian conjugate of the field.
Yeah.
But you in the interpretation.
Yeah.
You use T inverse, not the Hermitian conjugate.
Right, but this is also Hermitian too.
No problem in the derivation. Use the T.
You mean here? Yes, I use the T inverse because the general definition of doing a change of basis is through the invertible matrix. Yes, you're right, but since I picked the invertible matrix, which is also Hermitian, then everything sandwiched and worked out right. Sorry, was that your question or I still missing your question?
We're considering on your Hermitian matrix or not?
Right now, generally I can take the invertible matrix. And then if it's not Hermitian, probably your question is, okay, now looks like it's not just invertible, but looks like I have to have not Hermitian. And then the way I have to transform this guy is not in terms of inverse, but everywhere I see inverse, I have to replace with right? You can just do the proper change. Okay, so good. Change of basis is done. Let me let's understand a little bit of a meaning. So we're going to basically try to understand this one by one. So previously in the vial basis, the way we organized it was that upper two component is totally left-handed or negative velocity state, and the downstairs two component is totally 100% right-handed, and then which is the same as saying that there's a positive velocity state, right? Now in this rotated basis, which was the basis derived originally introduced, now if you look at it, upper two component that has both negative and positive velocity, and then also downstairs has both negative velocity and positive velocity states. It has both in it. Okay. Eventually, this will be useful. Eventually, I mean very soon, because now we're talking about a massive fermion, and one of the example can be like say electron or top quark. It doesn't matter. And then for massive particle, you should be able to go to the rest frame. Okay. So there's a massive particle traveling. We can always boost go to the rest frame, where energy is m, the mass, and then there's no free momentum. Okay. Nevertheless, electron in the rest frame that doesn't move at all. Nevertheless, this guy must have both positive and negative velocity state in it. And so eventually we'll see that this decomposition that has both negative and positive velocity in both sides will be useful in such a way that it is easier for us to explore the physics in the rest frame. Okay. We will see very soon, basically. Okay. Good. Now we can actually solve the derived equation with that introduction of change of basis. Okay, so now that's actually solved. Talk about one wave, not wave, one wave solutions. So equations of motion now in terms of four component field, writing this, which if you look at very carefully, you see this like run down here, which I just erased. The equation of motion basically is this. Where, just to remind you, this Laplacian of ith component is downstairs round I, okay? Because depending on up or down, there's a relative minus. I'm just reminding you that definition. I have shown that this equation is equivalent. So number one, since this equation, called the direct equation, eventually also imply that it satisfies Klein burden equation. What that means is that this system, meaning any excitation that comes from this psi eventually does satisfy relativistic dispersion relation where m plays a role of mass, which means that on shell, by which I mean the psi configuration that does solve this equation does satisfy this on shell dispersion relation. Okay, so therefore, energy and then momenta are related by this expression in terms of this mass parameter. Okay, so we'll stick to that. Good. Then let's try a plane wave solution. So by which I mean, I look at the solution to this equation, which is a function of space and time, that is proportional to a plane wave. So minus plus I p dot x, and then some proportionality factor. So right now, I'm just gonna look at first a positive frequency solution. And that corresponds to taking here minus sign in front, and then I will call the prefactor function to be u sub p, where sub p means it is a three momentum. Okay, so let me quickly remind you why minus corresponds to positive frequencies. Everything is maximally confusing, right? Notation, everything is mismatched. So the art of science is keeping track of minus. Okay. And then I'll explain why only three momentum matter, which is pretty quick to see. Let me first remind why this function sitting in front, coefficient function, depends only on three momenta. That's clear because I'm looking at a on shell. So on shell, four components of the four momenta is not all independent parameter, right? There's a single constraint equation that satisfies. So particle lives on this hyperbola because we talked about. There's only three independent data we need to sort it out. Good, that's done. What about that? So in quantum mechanics, obviously, you know that Schrödinger equation takes this form. Okay, so let me just take a positive frequency mode. Okay, I just took a positive frequency mode. And then obviously, if you just solve that thing is proportional to either the minus I omega t. So minus I omega something or minus I times et, that corresponds to the positive frequency solutions. I'm looking at that. Good. So now let's plug in and solve the equation. So far, so good? Okay, so let's plug in and get the equation. So equation of the motion becomes now, if you do that, so basically the equation to solve, right? So basically equation of psi turns into equation for u. And the differential equation for psi, as usual, if you do the transform, becomes algebraic equation for the coefficient, as usual, right? Okay, you're familiar with that. Okay, so we're going to solve this. So if you were to solve this one shot, I think it's possible, but we're going to take a slightly, clever path, as Coleman demonstrated. So what we're going to do is that because we're talking about massive particle system, we can go to the rest frame. Okay, so let's see. By the way, this expression, I did not pick particular basis. Meaning, this particular expression is valid either in the Weyl basis or Dirac basis. Okay, so let's go to the rest frame. So I'm gonna take P goes to zero limit. What that means is that energy goes to mass. So this term drops out because P goes to zero. This becomes M. I can cancel M here and there. So I get the following equation. So if I go to the zero momentum limit, I get this equation. So this coefficient profile or coefficient function now becomes a eigenfunction of this beta with a +1 eigenvalue. Good. Now let's remind ourselves two representations. So here, remember, beta in Weyl representation is 0, 1, 1, 0 here. On the other hand, in the Dirac basis, it has 1, 0, 0 minus. Okay, so far, again, I have not picked any basis yet. So now let's talk about which basis might be more useful in solving this equation. So this one, if I view this as again four component object, this one mixes itself up and down, right? But this one is clearly makes it flat diagonal. Okay, so that's the sense. Now this appears to be more useful when it comes to solving this equation when we went to the grass graph. Okay, so let's pick that one. So then, if I do a Dirac, by which I mean this is a 4x4 examining matrix, I just moved it. This is what I need to solve. Okay, and it's a picture show that this equation is basically this, and then I need to solve this equation. So if you decompose this U spinner or object as two component upper indices, a component, and then downstairs to component object, obviously this can be solved by setting this to be 0, because then 2 times that should be 0, and that should be 0, and then this is now 3. But this is 2 components vector, right? So I can just pick up 2 basis vectors that solve this equation. Okay, so therefore, I immediately write down the solutions of 0. And we have 2 basis vectors. So, and 1 with some normalization, which we're going to pick soon. 1, 0, looks like natural choice. And then second basis vector. Again, and 2, some normalization that we are going to fix. Done. Okay, so now we want to get a finite momentum solution. Okay, starting from here. Now, in order to do that, physically, what would you do? You have a solution with a 0 momentum, and you want to get the solution with a finite momentum. What did you do? You're not gonna do it. I refuse to look at finite momentum solution. How dare can we look at finite momentum solution? Okay, well, boost, right? We talked about Lorentz invariant field here. So if you know something at 0 momentum, you know what's happening at the finite momentum by boosting. We're gonna boost it. Okay, so let's boost. Are you with me? So I'm gonna boost now. You have to follow me, otherwise you're gonna lose me. All right. So let's do it. But do we know how to do the boost? Oh no. So let's refine that. Remember, Lorentz, we start out with the plus minus, right? 2SU2, and then angular momentum was the sum of these two. And then boost generator was minus I times the difference of these two. Right? No? Good. Thank you. So let's boost it. Catch me. I'm gonna boost this. And also, which I will do. Also, one thing that I haven't actually specified yet is this normalization factor. Okay. So, and then we want to pick up the clever normalization. Okay. So let's do it. So first, to determine so in order to determine the Lorentz covariant normalization, well, by which I mean the normalization that makes sense under the Lorentz transformation. That's what I mean. Let's note the following. So let's remind that with the u plus, we constructed a vector which took the form that has sigma bar u plus, right? And that's how we constructed the Lorentz invariant Lagrangian before. And then with the u minus, we constructed another one, which looked like this. Okay. Now, since Dirac fermion has both in it, these two as a whole sum can be rewritten as follows. So if I, for instance, B mu W mu can be, which let me define to call U of mu, can be written as U dagger, the U plus dagger, U minus dagger, sigma bar mu 0 0 sigma mu U plus U minus. Right? So again, I just combined this right this way so far. Why did I combine this in this format? Well, since at least in the Weil basis, this is nothing but four component spinner in the Weil basis, right? And then this clearly is a four component spinner dagger in the Weil basis. And in case you, do you remember? Okay. In case you remember, so I'm writing sigma that, and then this was like so. So now if you look at this, what is this? So if you look at this, this has 1 minus sigma. This is 1 sigma. Okay, that was the definition of sigma mu's. Okay, you see that therefore this as a full vector takes the form that this is Weil dagger Weil, because the zero component takes only the 1 and 1. So I'm literally taking the this product. But for spatial component, you see what I'm having is that Weil dagger, and then it's sandwiching minus sigma sigma object. That's nothing but alpha vector in the Weil basis. So that is alpha this. Good? Good. So what have I achieved? Starting from information about this, which you already knew how to construct a Lorentz vector out of the spinors. Here is the expression that that is nothing but a Lorentz vector, but constructed out of a four-component spinor. Okay, and because this expression is again manifestly invariant under changeable basis, as you see, if you insert t and t inverse dt, and then you compensate by the alpha vector transform. This is also same as in the Dirac basis. Okay. What does that mean? What does that mean? Well, again, the question started out with this expression. Okay. So then what we have done is that we started out by saying that okay, this looks like some u vector times plane wave vector. And again, this is only a function of this for momenta imposing Onshal condition. And then this expression only expressed in terms of u's. If I write again this, well, we talk about the two different objects. We haven't constructed this object yet, but we're talking about two different objects. So let me put R S 1 and 2, and then R dagger alpha S. So this looks like sensible four vector constructed out of the U's. As I just demonstrated, I just took the pre-factor here. Because exponential factors literally cancel out. So this is the same as that, right? For plane wave solutions. And if you wonder, this is true in both bases. As I said here, doesn't matter which basis you pick. Okay, are you with me so far? Does that make sense that this is a well-defined Lorentz format constructed out of this use? I just little bit short here. But it looks like everybody except a couple are totally lost. What's going on? Ask me if something's like that. Yes.
I'm questioning why you sum of V and W vector to construct the U.
Okay, what was motivation of doing that? Because since we knew this, and then since I know that the Dirac spinner, the four-component spinner has both this guy and that guy. So starting out with the two vectors, I want to construct another vector which has both in it. So here's one option to do. And then it turns out that this is indeed a sensible expression in terms of four-component spinner that we talked about. Good. Any other question? Yes.
What are the R and S in the superscript?
Good, thanks. So we say that, for instance, we look at this rest mass frame solution. We found out that that thing has that should span two-dimensional vector space. So we had a 1 and 2. So that captures the spin up, spin down degree of freedom. So whatever that object, a solution to the polynomial solution is a two-dimensional object. So therefore, there should be two different vectors. So I just, for now, introducing a notation to maintain or keeping notation for that those 1 and 2 components. Does that make sense? It's literally this 1 and 2 because it is a two-dimensional vector space. Good. Any other questions so far? Are you with me? Am I alone? Let's continue. I'm going to say something more. So now this is a sensible four-vector, Lorentz four-vector made out of these functions. Now, look at the expression. And all of you are looking at it. And if you look at this expression, what are the possible candidates for the Lorentz four-vector? This is a function of a p, right? And then spin. So my claim is that whatever that is, this should be proportional to, let me write it as this, proportional to four-vector of that particle state. And then I want to decide or construct my two-dimensional vector space in terms of two orthonormal vectors. Okay, so I want this to satisfy this property. Once again, P is the only candidate for the Lorentz four-vector because this is only a function of a P. There's no other Lorentz vector in it. Okay. Okay, let's. Does this make sense so far? Okay, so now if I reduce this down to the rest frame, so by sending P goes to 0 again, so that now I make a contact with these normal jet vectors. They will reduce down to the P0, sorry, U0 R, U0 S. There you go. Good. And then they should, reduce down to, now if I send this guy to the rest frame, it should be mass, and then vector, and then product of delta, imposing the fact that these two are orthogonal, as you see. So I constructed it in such a way that they're orthogonal. So if you like, I can just look at 1, 1, 1, 1. And that means that U dagger U, this guy, should be proportional to mass. So now you see that this normalization factor, I want it to be proportional to the mass. So I want to set this to be mass times some proportional factor C. And if you do the same thing with the U2, we find the same thing. So I want second one also to be some constant times mass. And we're going to fix that constant basically now.
이 P가 저 표현에서 P가 들어갈 이유를 다시 한번 설명해 주시죠.
Here?
Yeah.
Okay, the question was, given this expression, which looks like, oh my God, something, and how would I know that it should be proportional to P? That's the question. That's a good question. And this sort of thing will happen again and again and again if you, actually study more quantum field theory, right? So here is a left-hand side. Good, everybody's with me. Here is the right-hand side. And then left-hand side is constructed out of the function. And then that is only a function of three momenta, by which I mean it is a function of four momenta imposing on-shot condition. Remember, I explained to you why I'm writing P vector instead of P mu, right? Because there's on-shot condition. So if you look at this side, what is ever possible thing, object, for which this is dependent upon, has any Lorentz vector structure in it? This is only a function of momenta, and not even a function of two different momenta, only single momenta. So if I need to construct a Lorentz vector out of that, which I show that this expression is a Lorentz vector, momentum is the only thing that I can use to construct. Nothing else. So basically, I'm making a general statement that if somebody hands you a function of P mu, K mu, for instance, and then suppose I'm constructing a Lorentz vector function, right? Then we can ask, oh, can I write down the ansatz for this? Well, I can't, because it should be A times P mu plus B times K mu. What else could it be? Well, A and B may contain inner product, so that's Lorentz invariant, that's fine. So this can be a function of a Lorentz invariant, but all the vector structure should be captured by these two, nothing else. Good? Good, yes.
여기 대충 U 스퀘어가 n에 비례하는데 이거 루트 n에 비례해야 되는 거 아니에요?
You mean this, right? Yeah, that's what I meant. Thanks. Good. Right, because the square root is n, therefore u should be what the square root of n. Yes, that's good. Good? Okay. One. So we're going to fix now this C, because that's the only unfixed quantity, by actually now constructing a finite momentum solution from zero momentum solution by boosting it. Okay, so let's do it. So finite momentum solution with R goes 0, 1, and 2. It's two-dimensional space again. By boosting it into dot along the direction of the momentum, I'm going to boost it minus I a hat boost to generator angle and then acting on zero momentum. Okay. So this is a general expression for the boost acting on a spinner, right? That's what we talked about. And what is this thing? M, remember? Vector minus J plus minus J minus. Okay, so this is a general expression regardless of explicit representation. And then this is equal to, so if you let me write that answer and then just like that. So this is the same as that. So how do you see that? Let's go to the file representation. So in file representation, if you go to that, first of all, this guy is calling me U plus U minus, right? In file representation. And then you know how U plus minus gets active, because U plus gets getting transformed only under the J plus. U minus is transforming under the J minus, right? And that's exactly the label. So that means that a boost in this boost generator in this representation is nothing but this. So let me write it slightly bigger. This is gonna act on this component object. So the one that acts on the U plus should be minus I times generator, which is sigma over 2. right? Because of minus sign. And then the thing that acts on the downstairs is plus I over 2 sigma. And if you remember this, so this is minus sigma 0, 0, sigma, and that was exactly the alpha in file representation as I nicely raised. Okay, so this is true statement. Good. So now we know what to do. So let's rewrite this. If I plug in, I get e to the I cancels that, so that gives you 1 over 2 alpha vector, and then along the a direction with angle phi, acting on 0 moment solution. And if you want, let me remind you quickly, right? Given I don't know P of x, how does that get transformed? A boost under the boost? Well, it does. That's acting on the P x. Sorry, here beta. Well, beta is a b over c. And the gamma is 1 minus this object. Okay, so don't be confused with the rest of the beta. Okay, and then you also read this as how cosine hyperbolic of phi, sine hyperbolic of phi, sine hyperbolic of phi, cosine hyperbolic of phi, acting on t of x. Okay, so that's how you learn the boost, Lorentz boost, right? So in particular, this phi, which is a hyperbolic angle, according to this relationship, satisfies hyperbolic of phi is gamma. And the gamma in the relativistic energy relation is E over mass. Remember, for relativistic particle, energy is gamma times f, as you know. Okay, so that's the relation that keep in mind, that you need to keep in mind now to get the explicit expression. Okay. Good. Now, so we know how to construct the arbitrary momentum solution. This is the stability equation. Now let's actually pick a specific direction. So without loss of generality, I use the one fancy acronym. Any given momentum direction, I can call that to the z direction. Okay. So I'm just going to pick the direction of a propagation, which is nothing but this, literally direction of propagation. Let me pick to the z. So then the boost we get is e to the f alpha z phi acting on the u vector. Okay, good. And then, so in the rough basis that we are working, this is this, and then you can quickly check that square e squares to 1, just like sigma matrices. So therefore, this can be shown to be the same as cosine hyperbolic of phi over 2, and then as you have seen a million times in quantum mechanics class, sine hyperbolic of phi over 2 acting on this 0 moment substitution. Okay, so to be absolutely pedantically explicit, let's just write it down. So along the diagonal, because this is a proportion to the identity matrix, right? I have cosine. That means cosine phi over 2, cosine hyperbolic phi over 2, cosine hyperbolic phi over 2, cosine hyperbolic phi over 2. Done. And then alpha is off diagonal. Okay? So that gives me 0 to start. And then this sigma written with this. So that means, oh, hold on, no, stop. Minus sine hyperbolic phi over 2, sine hyperbolic phi over 2, because there's a minus sigma 3, right? And then sine hyperbolic phi over 2, sine hyperbolic. Okay, so that is this 4x4 boost matrix acting on 4 components game. Okay, in Dirac representation. You can do it differently. Good. So now we are ready to write down the solution. So let's remember this. So this is a zero momentum solution. Now we are about to fix this basically now. Let's rearrange this except class expression. So in order to fix that, what is the cosine hyperbolic pi over 2? Okay. So it's clear also what I'm writing. That is cosine pi plus 1 over 2. And then sine hyperbolic pi over 2, as you know, cosine hyperbolic minus 1 over 2. You can literally just check, right, by scaling this stuff. And then I told you this expression, right? So cosine hyperbolic can be written as energy and mass. So this is E over m. So I can just multiply m upstairs, downstairs. So that becomes E plus m over 2m. And then sine hyperbolic becomes E minus m over 2m. Okay. Okay. Good. We're done. So if I now take four component object, for instance here, okay, everything below 0 for positive frequency solution, I have either 0, 1, sorry, I have either 1, 0 or 0, 1. 1 picks out the first column vector. 0, 1 picks out the second column vector. Right? And then this has 1 over 2 square root of 2m normalization. And square root of n cancels nicely because of the Lorentz covariant normalization we talked about. So if I choose C to be 2, then it will nicely cancel out the entire denominator, right? Without having without having any unhappy one of square root of 2. So we're going to pick C to be 2. Then our final solution, finite momentum solution, will take square root of E plus m, 0, minus E minus m, 0. That's E U of 1, because I just take this guy and then boost it. Then the second one, by reading of the second column vector, is 0, E plus m, 0, E minus m. Good. So we solved it for a finite, for a positive frequency solution to the Dirac equation. Okay. Any questions so far before I explore more properties of this thing? Good. Okay. So first of all, immediate thing that you can check is, again, zero momentum limit, which you should be able to see immediately, right? So if I take the zero momentum limit, obviously you want to recover this guy, which is big, because in the zero momentum limit, E becomes m, so that's 0, this becomes 2m, that's exactly that, right? And then this is 0, this becomes 2m, that's exactly that. Done, obviously, so boost worked out as it needs to be. And now, since you have an explicit expression for solution and alpha vectors, beta, you have everything, right? You have an absolute explicit expressions. You have to be able to show now that the general momentum solution indeed satisfies this normalization. Is if we wanted to construct. Remember, I picked the C to be 2, so that's why it's 2 is sitting. You can check. So you can basically check 6 equations. 1, 1, 1, 1, this component, that component, 1, 2, 1, 2, show that that's 0. You just check explicitly as it needs to. But remember, the way we constructed that, I mean, this is a self-consistency check, right? It's not a derivation because we derived this expression anticipating this must be this, right? That's how I argue that this is the sensible normalization that we can talk about. Good. Any other questions? Any questions so far? Okay, so now since we have done this, then we can construct similarly negative frequency solution. That is now basically the same step. So let me just write down a result. So now I'm just gonna take ansatz that now this is plus I to the x. Yes, that is negative frequency. This time I'm gonna call the prefactor to be v of momenta instead of u. So you can plug this into the Dirac equation, and the equation should be P of P minus alpha P V is now minus instead of plus m beta. Okay, so compared to the positive frequency case, I just have this overall sign difference because here instead of minus, I have plus. So that's what you get. Again, you can explore zero momentum limit. So in the zero momentum limit, if I send momentum goes to 0, that 0 that becomes m cancels. Now you see that this v should be again eigenfunction of beta, but with -1 eigenvector. Okay, so previously we had u is an eigenvector of beta with a plus idea, and that's the difference. So in the Dirac basis, so this looks like 1 minus 1. So in the Dirac basis, you see that, therefore, the exactly equation that you have to solve is not 2, 0, 0, 0, acting on the v. So this is, I should have said 0, because this is 0. Sorry about the typo. Okay, 0 momenta. So therefore, viewing this as again 4-component guy, upper 2 should be 0, but 2 times something should be 0. Therefore, this guy only has non-trivial downstairs, lower component quantity. So again, then we can write it as the first zero moment solution is 2m, because we now know what's the right combination, and then second line. Like so. Okay? Take the 2 basis factors. And then you can boost to get an expression that looks like this. Basically. Same thing. This is the same expression. So for instance, V1 is boosted because it has the last one component according to that. You get square root of E minus m, square root of E plus m. This guy, since it has a 1 and the third component, you will pick up this. So minus of square root of E minus m plus square root of E plus m. That's the answer. Okay? Done. In case some of you have noticed something, have you noticed something weird or not so far? Totally happy? Good. Then we move on. If some of you mentioned that, like some erase this, I will mention that. Otherwise, we move on. And this time I made it. Okay.
그냥 공부해서 그런데
네.
저기 V1에서 아래쪽에 1,0을 1,1
Very good. Phew, the whole class was rescued. Yes. So, like, what's wrong with me, right? Why am I picking this way instead of I call this to be V1, this to be V2? Right? Good. So let me explain that. So eventually we're going to quantize this theory. So let me remind you that the scalar field that we constructed last semester, take this form. I mean, the exact detail is not important, but let me just write. Scalar field that we constructed the last semester, look this one. Was the launch condition. So what was the physics of that? There's a positive frequency part that annihilates the particle, right? And then there's a negative frequency part that creates the antiparticle, right? Good. So there is a particle, antiparticle. There's annihilation, there's creation. Good. So that's what we talked about. Now, so for fermion, we're going to have a similar expression. Let me just write. This is normalization, don't worry about it. I mean, we talked about it, in principle, you already figured it out. But, we'll discuss this pretty soon. So what's the physics here? There is a annihilation of a particle, for instance, with helicity, because this has helicity in the quad. This has spin is better. Spin up or down, because that has a two components here, right? Spin up and down. So let me just write it as a plus half and a minus half. And then this is antiparticle parts. This is creation of antiparticle of what? So this is related by charge conjugation. And if you recall, given a, say, half zero representation under the charge conjugation, this turns into that. Also P2. So it's under the C or P, this flips. So if I have a particle with spin up, under the charge conjugation, I have to go to the antiparticle spin down, and vice versa. So if I had spin up particle under the C, I want to map that onto the V1, which is a spin down. Okay, and vice versa. So that's why. Like, almost that shows. Okay. All right. Now we move on to the next subject. Not subject, but now the remaining of time today. Make sure. This ends 4. Yes. Right. 4. Right. Okay. Let's make sure. So we started out this lecture by saying that there's a nice way of packaging Dirac Lagrangian as like so. Then we talked about going from the vial to the Dirac and sonators. So is it just notational, simplicity, or there's something more than that? Okay, so that's the part that I want to discuss the remaining of the time. So that's not a coincidence. Okay, so number one, we can check that alpha, beta satisfy the following expressions. So alpha I, alpha j is 2 times by j, alpha, all alpha anti-commutes to the beta. By the way, this notation is if I have A and B, instead of this square bracket, which is commutator, this curly bracket is that. It's called anti-commutator. And then finish up, beta is 2. So the statement number 1 is that yes, we introduced the notation, and somehow that notation satisfies this, interesting looking algebra. So this algebra is called. So this algebra is everything called a Dirac or Clifford algebra. So far, an observation. So now my job is to turn this observation into something deeper. Okay, so so the claim that I want to show is this. So I mean, I didn't know it is called the Pauli theorem. I knew the facts, but it is apparently it's called the Pauli theorem. From Coleman. So first, I'm going to state the mathematical fact, and then I'm going to state a physical implication of that statement. So this theorem says that take this algebra. Suppose you have a set of alpha, which is three 4x4 matrices, and then there's a 1, which is 1 4x4 matrix, right? By the way, this notation is just simply means that beta equals to 1, identity matrix. So the first statement is that any set of 4x4 matrices, which let me just package into beta alpha vector. Okay, so I'm packaged it. This is not anti-commutator. Is that very confusing now? No. Okay, I did it again. This is not anti-commutator. I'm just packaged it. Okay? Good. Any set of these 4 matrices. Okay, I lost. Is equivalent to the vital representation. So earlier, I introduced both wording. Like one I called, the vial basis description or Dirac basis description. At the same time, I also introduced that I am in the vial representation or Dirac representation. What it means is that given an expression, which I doesn't quite, picking up a specific expression for those matrices, I'm saying that given this algebraic mathematical algebra that these guys satisfy, suppose I found out those 4 set of matrices that satisfy this algebra. Okay, I'm saying that any set of those 4 matrices eventually equivalent to the vial representation we originally talked about. So vial representation had a form that there's a minus sigma sitting that, and then beta vial was this. So hopefully you understand what I mean by equivalent, right? There's a similarity transformation that brings arbitrarily those guys eventually to this guy. That's what it means. This is a mathematical statement. Now, is there a question? Yes.
So if the set satisfies the equation,
Yes.
and the set can be connected to the vital equation by unitary transformation, am I right?
By invertible transformations. Yeah. As a definition of similarity transformation. Yes, that's what it means. Yes. Any other questions? Okay, but let me now state a more physical meaning of this statement. Okay. So physically, what it means is that the entire structure of perhaps 3 Fermi theory is determined by these arguments. So more specifically, this particular sentence means that all reducible representation plus U of X group with parity variance as an extra condition. Containing spin half state or spin half particles. Are equivalent, eventually, hence this connecting sentence, this little h. And any long sentence equivalent set of this 4x4 alpha beta, once again, not anti-commutator. Finds same okay, anyway, feel like that's the longest sentence I ever written in the book. Let's go back and appreciate the meaning of that. Okay, so let's understand. This is a very long sentence, but at least I want you to understand the meaning of this. Okay, what does that mean? So mathematically, it says that okay, here is algebra. Hand me any set of those alpha beta. That better be equivalent to that. There must exist a similar transformation. But physically, what it means is that oh, I want to tell the theory of fermion. How do we start it? Here's the Lorentz group. We studied the representations, and then we introduced two-component object as a minimal component, and then we say how to construct the Lorentz invariant, real, blah blah blah, and then one derivative action. That's how we have done it. More theoretically, though, whole point is that the entire structure basically can be fixed or determined once somebody hands you this. Okay, so that's the argument that I have to show. So statement, just to understand the statement is this. This, if somebody hands you this, A, one should be able to construct a representation under which spin half particles transform. Okay, and if you find any representation of this Clifford algebra, then if you find really different representation of this thing, okay, eventually they're all equivalent and they all describe a single same Dirac Lagrange that we have written down. Therefore, this is, if you like, this is the beginning of the entire fermion theory, if you want. Okay, so that's the statement. Looks like I have to show this argument next time. Basically, what I'm going to do is that starting out by saying that, oh, I haven't found this set of matrices satisfying Clifford algebra. I'm going to show, oh, I can construct a, first of all, generators, and then lines in terms of those guys. And then I show you there is a consistent way of constructing it, entire Lorentz algebra. If I write down this and then bootstrap rest of the algebra, just using these properties. So the set number one, I show there is a way of generating Lorentz generators, satisfying all Lorentz algebra just by looking at the properties alphas and betas. That's step number one. Step number two, I show that that representation of the Lorentz algebra necessarily is for, that's step number one. Step number two is for pairing invariant is the Dirac system, okay? And then finally, I show that for any given alpha beta, indeed, one should be able to find a similarity transformation that always bring, and you can bring this to the file basis or file representation as particular mathematical statement is saying. Okay, but the first part is actually more physically important statement. Okay, so for any given those alpha beta sets like that, you can always construct a Lorentz representation, and that representation is not random, but always the system of trust. Okay, so that's the thing that you will do next time. and then we'll move on. Okay, that's all for today.